We're here at the example table, and in this video we're going to talk about graphing radical functions. This is something that's hard to do in general, so in this video we're going to stick to some simple examples to illustrate some general points. Let's start with the function y equals x to the a power, and we're going to assume that a is greater than 1. So we're going to get to radicals explicitly later on, but you could think of a as being something like 5/2, right? So then this is the square root of x to the 5th. So this is going to be a radical function for most of the a's that we care about. Let's sketch just the graph in the first quadrant. If a is 1, I know I said a is greater than 1, but if a is 1, this is just y equals x. But if a is, say, 2, then this is x squared. And let's actually label. We need some points. Let's set this equal to 1. So that's right here. So we know that this graph passes through 1, 1. And in fact, for any value of a that we care about, this function evaluated at 1 will be 1. So all of these points are going to pass both through the origin and through this. If we graph y equals x squared, so a equals 2, we get a parabola, and that looks something like this. So this is a equals 2. If we set a equal to 3, then we get y equals x cubed, and we get something that usually we think of as looking a lot like a parabola, but it's not quite the same. So this one is a equals 3. That's x cubed. And you can see a general pattern emerging. As a gets larger and larger, the function between 0 and 1 is getting pushed further and further towards 0. So we can think about this. Take an example, 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. Likewise, 3/4, 1/4, any other value you want to take, between 0 and 1, as we increase a, these values are going to shrink towards 0. Now let's think about what's happening on the other side of 1. If we take some example point 2, then 2 squared is 4, 2 cubed is 8, and we can see this pattern holding no matter what point we choose, and no matter what values of a we choose. If they're increasing, then the function values on this part are going to get larger. And so that's why this green curve is above the red curve once we get past 1. But between 0 and 1, the green curve is below the red curve. You might ask what we could do if we let a equal something that we don't know how to handle yet, such as pi. What could x to the pi mean? Well, that actually is a topic better left for calculus, but you could get some indication by saying that x to the pi is going to live somewhere between x to the 3.14 and x to the 3.15. So now that we know roughly how these things behave for a greater than 1, let's talk about how they behave for a less than 1. So we're sticking with the same function, y equals x to the a, only now a is going to be less than 1. We're going to bound it below though by 0. So we're thinking of a being 1/2 or 1/3 or 2/3, something like that. Now, if you need to review inverse functions, you should probably do so now. But we know from what we know about inverse functions that we could start with say to get the graph of y equals x to the 1/2. We could start with the graph of y equals x squared, which was this parabola, remember, and we could flip it about the line y equals x. So y equals x to the 1/2 looks something like this. This was supposed to pass through that point. And what about, and so this is a equals 1/2. And what about a equals 1/3? Well, that corresponds to y equals x cubed, and we remember that looked something like this. So if you imagine taking this graph and flipping it and rotating it like this, we get the graph that we had before. So the green curve is this thing coming from here, a equals 1/3. It's going to be closer to the y-axis when we're between 0 and 1 on the y-axis, and it's going to be further away when we're above 1. Now let's take a look at a few concrete examples. Let's start with something that's familiar. We've effectively already talked about this. Y equals the square root of x looks something like this. And notice that the square root of x is only defined for the positive values of x. Think of this as being one branch of a parabola, right? We have the parabola y equals x squared looking like this. If we invert it, we get a parabola facing this way, and we have to remove the lower branch to make it a function. So that's why this square root of x defaults to the positive value. What, on the other hand, happens if we take cube root? Well, the cube root isn't restricted. We can take y equals x cubed and rotate it. We get a graph that looks roughly like this. Now let's try to combine this with what we did before to see what happens when y equals x to the 2/3. So this, if you are more comfortable, you can write this as the cube root of x squared. And this will have an advantage in a moment that we'll see. So we know that x equals x to the 2/3 is going to look something like this, right? And if we wanted to be more detailed, we could draw y equals x squared on the same plot, and we could see whether it's above or below using what we did before. But for now, this suffices. A is less than 0, right? Less than 1. 2/3 is less than 1, so we know we're going to have a curve opening like this. But let's look at this formulation. We have x squared, which means that the output can't tell whether we plug in a positive or negative value. This means this function for negative values of x looks the same as it does for positive values of x. Another way of saying this is that this is an even function. So knowing what it looks like here necessitates that it looks like this here. So we can see that with radical functions, we can get some we can get some behavior that's not possible with polynomials or rational functions. Such things never lead to a pointy part like this, but we can get these with radical functions.